Okay, so from this lecture, let's start a few discussions on group theory. So, uh, you know, we have a complete playlist discussing about linear algebra, and I'm very much intended to make such a playlist where I'll be covering all major topics on group theory. Now, previously, I have been discussing about a few important topics of group theory, but my main focus was the group actions, right? So, you know, now throughout the discussion, I will assume that you guys know what a group action is, at least very basic knowledge about group action. So, the other important topics will start from today, and we will go, we will start from the very basics of groups. Introduction to groups are very trivial. I'm not going into those details. So, we will start our lecture from the concept of subgroups precisely. And this lecture is fairly intended to, we will be starting from subgroups, and gradually we will be, moving into the more abstract concepts of group theory, just as we did in the case of linear algebra. So let's start. So we will discuss the concept of subgroups first. Okay, subgroups. Okay. After covering the major concepts regarding subgroups, we will move into something which we call the quotient groups. And obviously, you know any abstract structure or any space, to be precise, you study in the case of maths, we always try to fundamentally construct two such objects out of the objects you study. One is something sort of a sub object, and something sort of a constructed object which we call the quotient object. These terminologies will be a bit vague, but as we study the concepts of subgroups, we will get somewhat sort of an idea of what did I mean by the concept of sub-object, and what did I mean by the concept of a quotient object. So let's start from the concept of subgroup. So let G be a group. Okay, let G be a group, and throughout the course, I'll use the convention of G being a multiplicative group. Obviously, if in any case we require G to be an additive group, I'll obviously mention, or you people will obviously understand that I'm considering G to be an additive group. Okay, so let G be a group. So we consider a subset of G. So let me just decrease the size a bit. Yeah, okay. So a non-empty subset of G is said to be a subgroup of G. Okay, and the definition is very trivial. That is, if H is a group, if H is a group under the same operation as G. Okay. For example, we know that Q is a group with respect to your basic arithmetic operation, basic arithmetic additive operation, right? Now, Z is a subset of Q, that is precise, a non-empty subset of Q. And if you consider elements from Z, then you will obviously observe that Z itself forms a group under the arithmetic additive operation. That's quite very basic property. So indeed, Z is a subgroup of Q. Similarly, Q is an additive subgroup of R. R is an additive subgroup of C, and the concept is very simple of that sort. There is nothing that difficult to understand the concept of subgroup, provided it's indeed a group. Just it is a subset of a given group, and the operation stays the same. That's it. That's the concept of subgroup. And any object you study in future, a sub-object of that follows the same rule. Okay, it's very similar to the object you are studying, or I should say it's exactly similar to the subject you are studying, to the object you are studying, and the sub-object carries the same properties as the higher object. That's the sort of concept you have for a substructure, for a subgroup in this case. Okay, so one thing is very obvious from here, that the identity element in a subgroup is same as the identity element in a group, because the cancellation laws hold in the subgroup as it holds in the group, right? So let me just state them of observation. You can try and prove them on your own. Not quite a difficult task. Number one, that the identity of G is same as the identity of H. Okay. Number two, um, if you choose any element from G, then the inverse of that element in G is same as the inverse of that element in H. Okay. So X inverse in H, that's the notation I would use, is same as the inverse of X in G. Okay, and this happens for all the elements X in G, or I should say X in H, because X being in H automatically means X is in G, and that's more precise, right? Okay. Um, One more important example in the case of subgroups, I would say, is like you people know what a dihedral group is, right? So precisely, it's a group of the following form. I should say it's a group generated by uh, two elements R and S, which obeys the properties that R to the power n is 1, S squared is 1, and R times S is same as S times R inverse. Okay. Uh, it has a high geometrical, importance. It is merely the collection of elements, collections of, I should say, symmetries of n-sided regular polygon. These are the elements are they precisely, you know, indicate the or determine the rotations possible from vertices to vertices in case of an n-sided polygon, and S determines the reflections possible of over a n-sided polygon, right? But obviously maintaining the symmetry of the polygon, the shape of the polygon must not change. Okay, we will cover this dihedral group. I am trying to cover this dihedral group specifically in a individual lecture. Like we have done the, I guess we have discussed the concept of a permutation group in great details in a very specific lecture. I'll do the same for a dihedral group. This is specifically called a dihedral group for a n-sided polygon, to be precise, and its structure is quite like that. If I explicitly write the elements, so let us choose a smaller group. Let's choose D6. So in this case, obviously, you can observe that n carries the value 3. So it's sort of 1 r squared, because r cube is 1, right? And then you have S. You don't have S squared because S squared is 1. So you have SR squared, and that is the number of elements. So you have 6 elements in total, right? Okay. So in D2n, or let me consider these D6 only. If you consider the subset 1 r squared, then you can obviously observe that this is a subgroup of D6. This will be notation I will using for subgroups. Okay, this forms a subgroup of D6. Um, it's very easy to check that it forms a group structure. Okay. For example, if you choose NZ, let's say, so let this be example 1. Consider example 2, 2Z, let's say. 2Z is a subgroup of Z. But you observe that 3Z, is 3Z a subgroup? Is a subgroup of Z? That's my question. Is 3Z a subgroup of Z? So for 3Z to be a subgroup of Z, 3Z needs to be, a group, to be precise. You'll observe it's indeed a group. Is it so? check on your own. What more can you what more conclusion can you draw out from here? What can you say about nz? Okay, n is any integer. Let's precisely n be a positive integer. What can you say about nz? Is nz a subgroup of z? Okay, that's uh, okay. So okay. Um, Now there is a very nice claim, and this claim is pretty obvious that if I consider the concept of subgroup to be a relation, for example, then this relation is transitive. Okay, what I mean by saying is that let M and N be subgroups of G of a group G and let sorry, let me not claim it like that. Uh, let me change the notation in a way. Let G be a group. Let G be a group, and let M be a subgroup of G. Okay. Let G be a group and M be a subgroup of G. Then if N is a subgroup of M, then N is a subgroup of G as well. That's the precise claim. Okay. So what I mean is that if N is a subgroup of M, M is a subgroup of G, then that implies N is a subgroup of G. Clear? That's pretty obvious, right? Because if N is a subgroup of M, so N is obviously a subset of M, and N has the same group structure as M. Sorry, the same group operation as M. M is a subset of G having the same group operation as G, indeed forming a group. So it carries over to N as well, right? It's a very obvious claim. Okay. Now, suppose G is a group. Let G be a group. Obviously, as I just said, that we are considering the a group to be multiplicative. Okay, so what can I say about the set containing only the identity element? Will it form a group? You can obviously observe that if G was an additive group, then we would have considered the element 0, the set singleton set 0. Okay, what can I say about this group? Okay. So the only element here is 1. So it obviously obeys the closure property, because 1 times 1 is 1. Okay, 1 itself behaves as the identity. The inverse of 1 is 1. 1 multiplied to itself any number of times is associative in nature. So indeed it forms a group. I should say a subgroup, right? What can I say about the group, the whole group G itself? Indeed, every set is a subset of itself, right? So if every set is a subset of itself, and G being a group, it means that G itself is a subgroup of itself, right? So any arbitrary group you take, it will always have two subgroups for sure. One is this identity subgroup, which contains only the identity element, and one is the whole group. So these two are called the trivial subgroups of G. Okay. So let me just state it as a definition. Let G be a group. Let G be a group. We say that the identity set and the whole group are the trivial subgroups of G. I shouldn't have used the term a definition, because that's sort of a statement. Are the trivial subgroups of G. Okay. Any subgroup of G other than these two are called the non-trivial subgroups of G, and that's quite obvious, right? Okay. Now our concern is that if we are given a substructure of a group G as a subset, let's say we are given a subset of group G, then what are the least possible calculations to do to check whether the subset is a group or not? Like if we are given a group and we are given a subset of it, it's not quite efficient to check every axiom of it being a group, right? So we come to what we call this the subgroup criteria, you might say. can go to the next page. Okay. So what is the subgroup criteria? Subgroup criteria. Okay. So let G be a group. Let G be a group. Then H contained in G is a subgroup. Is a subgroup if and only if the following two conditions hold. The first one is quite obvious, that H is non-empty, and number two is that for all elements X and Y in H, X, Y inverse is in H. Okay. So if only these two criteria hold, then we can say that H is a subgroup of G, because these two criteria are sufficient to check every group axiom for H. Okay, let's just prove it. What happens if H is a subgroup? Then it's obvious, right? If H is a subgroup, then it's obvious, right? Because if H is a subgroup, then trivially it's a group, so it obeys the closure property. It has the inverse. So statement 2 and statement 1 are obvious because it's obviously non-empty for it being a group. What happens if these two conditions hold? Okay, so let H be a subset of G such that 1 and 2 hold. 1 and 2 hold. Now, obviously, since H is a subcollection of G, of the elements in G, associativity holds trivially in H for every element in H. So that's not something which we need to check. We need to check about the existence of identity in H, the existence of every inverse of every element in H. That's precisely. If G is abelian, that is G is a commutative group, then the property of commutativity also holds trivially for every element in H, because H is simply a subcollection of the elements in G. Right? So that is also not something which we want to check. So we need to check only three properties specifically. One is whether H is closed under multiplication. Obviously, again, I am telling that we are considering the group multiplicative. Then we need to check whether the identity is there in H, and whether the inverse of every element is there in H. So precisely that's what we need to do. Okay. So let's start. So first, what we do is, so let X be in H. Now, if X is in H, then by 2, X inverse must be in H, right? It's obvious. But X inverse by definition is 1, so 1 is in H. This also quite proves the fact that the identity in H is same as the identity in G, right? Okay. So, like this, the identity in a substructure is same as the identity in the bigger structure is not obvious in the case of larger abstract objects. For example, when you study rings, you will get that the identity element differs, okay, in a subring. Let's not go there. Okay, so 1 is in H. Now if 1 is in H, then for all y in H, 1 dot y inverse is in H, which implies y inverse is in H. So every element has an inverse and the identity is also in H. We are just left to check whether the closure property holds or not. And that's quite obvious because, let X be in H, Y be in H. Since Y is in H, Y inverse is in H. We have just proved that. If Y inverse is in H, then X, Y inverse, whole inverse is in H. But Y inverse, whole inverse is nothing but Y. So X, Y is in H. So H is closed under multiplication. H has identity, H has inverse. The other properties of group axioms hold trivially. Therefore, H is a group and hence a subgroup of G, because the operations are same, obviously. Right? Okay. Now, so we have not yet said anything about the finiteness or infiniteness of G. This subgroup criteria obviously holds for any cardinality of G. What if G is finite? Okay. So if G is finite, it suffices to check. It suffices to check that for all xy in H, xy is in H. That is, it suffices to check whether the closure property holds only. We do not need to check whether x y inverse is in H. Okay, and what is the reason behind that? Because um if you start with a finite group, then obviously a subset of it will also be finite, right? The claim is very obvious that if G is finite, then you know then if X is in H, where H is a subset of G, or I should say a subgroup of G, let's say, then x squared, x cubed are all in G. Sorry, all in H, right? So if they're all in H and H is finite, therefore there should exist some integers a, b, such that positive integers a, b, such that x to the power a equals to x to the power b. Because if not, then the powers of x will continue to increase and H will eventually become an infinite set, because it will contain infinite powers of x. So the powers of x must coincide at some point. So it coincides like this, let's say, and let's choose b to be greater than a by the well ordering principle of integers. It's quite without lots of generality. But this implies that if I choose n to be b minus a, this implies that x to the power n is 1. Well, let's say n is equals to b minus a. But if x to the power n is equals to 1, then we can write it as x times x to the power n minus 1 is equals to 1, holds obviously due to the law of exponents. Right? But if x times x to the power n minus 1 equals to 1, then that implies that x inverse is nothing but x to the power n minus 1. Right? So inverses hold trivially in case of a finite group. So it suffices to check whether closure property holds only. Right? Okay. Yeah. So we have discussed enough about subgroups. Let us now give three very major examples of subgroups. Okay. Okay. So these are called the centralizers, normalizers, and center of a group. Okay. Centralizers, normalizers, and center of a group. Okay. So we start with a group. Let G be a group. Then we define for a set, for a non-empty set A in G, the centralizer of A as, we denote it as C, let us use this notation, CGA. So it's defined as the set of all elements in G such that x A x inverse is equals to A for all A in capital A. Okay. Or we could also define it as all the elements x in G such that xa is equals to ax for all small a in capital A. Precisely, it's quite obvious to observe that this is the collection of all the elements in G. This is the collection of all the elements in G which commute with every element of A. Which commute with every element of capital A. Okay. Clear? Yeah. So the basic fact is that it's quite obvious from here. Let me just state the observation first, then we are going to talk about what I was trying to say is that if G is abelian, if G was abelian, then observe that for all subsets of G, obviously non-empty subsets, the centralizer of A exactly would be equal to G, because since G is abelian, every element commutes with each other, right? So whatever subset, whatever subcollection of elements I choose from G, every element of G will commute with every element of that subcollection. So that means the centralizer is equal to G. Or you can also check it out from here, that from the definition of a centralizer, the centralizer of G, of a set A is contained in G. That's quite obvious. If G is abelian, what happens? So let small g be in capital G. Since G is abelian, Gx equals to Xg for all x in G. But this implies GA equal to AG for all A in capital A, because A is a subcollection of G elements in G. So that implies G must be in the centralizer of A in G. Okay. So we have a both-sided inclusion, hence they are equal. We say this to be the centralizer of A in G. Okay. So the importance of a centralizer obviously lies in a group which is non-abelian, right? And what actually are we trying to do is that we are trying to gather elements which has the capability to commute. That's the only thing. Because elements which commute, they obviously possess a very special character throughout any arbitrary structure you study. They'll obviously contain, possess very important characteristics. You'll obviously, get taste of some of those characteristics in this course as well. But actually, the elements which commute do, they are very important actually. Whatever. Our claim is that centralizer of any subset A in a group G is a subgroup of G. Okay. So claim for all non-empty subset A of G, the centralizer of A is a subgroup of G. Okay. How do we prove this? Proof is again very simple. So we need to go through the subspace criteria. Obviously, the centralizer of A is non-empty. Why is it so? Because 1 is in the centralizer of A, right? 1, the identity element, it commutes with every element, right? Because any element you choose from A, 1 times A is A times 1 is equals to A. So the identity element of G, it commutes with every element of A, whatever be the subcollection A. That means the identity of G is inside the centralizer of A in G. Hence, it's non-empty. So the first point of the subspace criteria is, it is holding trivially. What about the second part? Let X and Y be in the centralizer of A in G. To show XY inverse is in the centralizer of A in G. Okay, let's check it out. Okay. So if X is in the centralizer of A in G, then since X is in the centralizer of A in G, so XA is equals to AX for all small a in capital A. Similarly, since Y is in the centralizer of A in G, YA is equals to AY for all A in capital A. Right? Okay. What are we trying to do here is we just left multiply with Y inverse on both sides. So we get A is equals to Y inverse AY for all A in capital A. What we do is we impose this here. Okay. Then XA equals to AX implies X times Y inverse AY is equals to AX. So this implies by associativity XY inverse AY is equals to AX. We write multiply by Y inverse. So we have XY inverse A is equals to AXY inverse, and that immediately says that XY inverse is in the centralizer of A in G. Therefore, by the subgroup criteria, am I being using the term subspace criteria? No, sorry, subgroup. Yeah, obviously by the subgroup criteria, this implies that the centralizer of A in G is a subgroup of G. Okay, clear? Fine. Okay, we are not going to extend this lecture much. Before ending this lecture, let me just briefly give out the definition of the two more terms which we have introduced here, that is the center of a group and the normalizer of a set. Okay, so let G be a group, let G be a group, and let A again be a non-empty subset of G. We define the normalizer of A in G as, so we write it as NGA. So this is the collection of elements small g in capital G which commute with the whole set, such that G capital A is equals to A capital G. Or a better way of writing it out is that we can write it out as G capital A G inverse is equals to capital A. Okay. What is this set? So G capital A G inverse, it is defined as collection of elements in the form G A G inverse such that A is capital A. That's it. Okay. Now, one thing which you guys might think is that G capital A G inverse equals to A, and G capital A G inverse is defined as G small a G inverse, where small a represents arbitrary element of capital A. This might imply that G A G inverse is equals to A, right? For all A in A. So what should be the difference between normalizer and a centralizer? Precisely the fact doesn't lie like that. In case of a normalizer, G capital A G inverse is equals to A. This merely means for some A1 in A, there exists some A2 in A such that G A1 G inverse is equals to A2. So these two elements need not coincide. That's the problem. Okay. So it is not exactly same as a centralizer. Indeed, if you have a fixed subset A, then the centralizer of that subset A in G is a subgroup of the normalizer of that subset A in G. Okay. We will be obviously discussing this in the next lecture. In the meantime, you can try and prove it on your own. That's quite easy to prove. Okay. Actually, showing that the centralizer is a subset of the normalizer suffices. If you show that the normalizer is a subgroup of G, that's told from transitivity. What is the center of G? So it is defined as the elements in G such that it commutes with every element in G. Okay. So this is a broader structure for a centralizer, nothing else. That is, it is merely the centralizer of the whole group G in G. Right? It is the centralizer of the whole group G in G. That's precisely the center of G. Right? Okay, we will explore more about these structures in the next lecture, and we will be also discussing about two very important terminologies which are merely used in group actions, which are called the stabilizers and the kernel of a group action. Okay, so meet you guys in the next lecture.